Okay, so I wanted to go through this lesson. There wasn't an answer key per se, but I wanted to go through it and discuss with you why we got some of the things we got and see if that helps you connect all of the pieces together. So when you went to table one, if you used the simulation correctly, these are the answers you should have gotten. And one thing I want you to notice is that for everything in this table where there are no lone pairs on the central atom, we can see that our molecular geometry, our molecule geometry, and our electron geometry are exactly the same. They have the same name. That'll be important later. And then we also have the bond angles. Now, you'll have your notes. If we were in person, I'd say you'd have to have this committed to memory one way or another. When we had two atoms attached, so actually I can use this molecule to help me. What we're doing is we're taking this invisible circle. I actually don't know if it's showing up, so let me draw. We're taking this like invisible circle around the central atom, and we are splitting it into two parts, right? This kind of line divides it in half. And so when we're thinking about the angle between the two, if you think of a circle being 360 and we divided it into two parts, well, it makes sense that 360 divided by 2 would give us an angle of 180. Similarly, when we're working with three things attached, so central atom, 1, 2, 3 atoms, if we actually showed on the simulation how these would spread out in space. My drawing isn't perfect there, but we took a circle and divided it into 3 parts. This part, this part, this part. And so that's where the 120 comes from. When you have tetrahedral, let me actually show you on the simulation, 4 atoms attached. We're now kind of working in 3-dimensional space. We're not just sort of flat like we were, let's see, here, where you could lay this flat on a piece of paper or stick it flat up against a window, for instance. So when we have 4 things attached, we're now working in 3-dimensional space, and we're not just working with a circle. So that's why 360 divided by 4 doesn't work. I've had students mathematically prove why it's 109.5. I've never done that myself, but go for it if it helps. Okay, so that's what you should have for table 1. What I wanted you to see when you built both of these atoms is that they're both called linear. Again, I didn't specify molecular or electron because they have the same name if all we have are atoms attached and not any lone pairs. So when you look at this and when you look at each of these, one has single bonds, one has double bonds, but they both come out at linear, no, the type of bond, single, double, triple, doesn't affect how we answer any questions on this. It affects if the Lewis structure is correct or not, but not how we'd answer questions about this shape. Then when we moved on to table 2, and now we do have lone pairs on the central atom, it gets a little more complicated. So part of what we wanted you, first of all, check and make sure your answer is correct. Make sure that you actually did this bullet point and went back and put the less than sign. Anytime there are lone pairs on that central atom, your angle should have the less than sign. And let's talk about the rest of these questions. So, sorry. Okay. What do the 2 types of geometries with 4 electron domains have in common? Well, these are the ones with 4 electron domains. If I look across those rows, I see that they're both called tetrahedral and they both have the same angle. If you look back at table 1, we can try to figure out this whole parent structure thing. So looking back at table 1, do I notice anything similar? When there are 4 atoms attached, we call it tetrahedral and 109.5. So whatever words you put it in, like as long as it was in your own words, you're fine. But let me show you on the simulation. When we start with tetrahedral, 4 atoms attached, you'll notice its molecular geometry and its electron geometry have the same name. If I swap out one of these atoms for a lone pair, so I'm going to get rid of one and swap it out with a lone pair. There are now still 4 electron domains, 4 things attached, the 3 atoms and the lone pair. So it's like it's tetrahedral. It's based off that structure of tetrahedral where I guess I have 3 things coming out in this kind of tripod shape and 1 thing coming out the top. It's based on tetrahedral, but it's not exactly the same. And that's why we have this new name of trigonopyramidal. If again, I take another one of these original, like we started with here. Oops, too many devices. Starting with tetrahedral, but let's replace 2 of them with lone pairs. We still have that same little, it's kind of hard to see, but that same little tripod on the bottom with something out the top. We still have that general shape, so we still call it electron geometry tetrahedral. It's still based off of that structure of tetrahedral, but it now has the name of bent, because if we actually look, if we pretend that the lone pairs are invisible, if we actually just look at the shape the atoms are making, boom, what we see here is a bent line. That's another reason that we have 2 types of bents. So I think one of the other questions gets at this. If we only had 1 lone pair, see how the shape didn't change much? The angle changed slightly, but between this and, oops, whoa, I didn't mean to do that. Between, hold on, let me re-rotate it. When we had this bent structure that was based off tetrahedral versus the bent structure that's short a lone pair, now this only has 3 domains. That's why it's based off trig planar, 3 domains. But it's still called bent because, boom, that shape looks pretty much the same as when we had 2 lone pairs. I just have to rotate the image. So that's why there are 2 molecules with bent. They have different angles because they have different parent structures, different general structures that they're based off of, as if they were all atoms, but swapping out some of those atoms for lone pairs. Let's see if there's anything else I want to talk about. Yeah, so another way of looking at that similarly is if we're looking at linear molecules and then the 2 bents. Look at that here. This is a linear molecule, 2 atoms attached. One of the bents is like that, and one of the bents is like that. So when we have 2 atoms attached, we still end up with 3 different angles. Let me do that again. 2 atoms attached, the angle's 180. 2 atoms attached, the angle's 120. 2 atoms attached, the angle's 109.5. But what did I change from each of those structures from one to the next to the next? The number of lone pairs on the central atom. So hopefully that helps. What you might want to do in terms of your notes, you might, if you had trouble connecting this to lesson 3, the one we did is a Monday this year, you can make yourself a little summary. So not using the formal language, but looking at the number of things attached might help. Just be very clear that what I mean by things are either atoms, so again, single versus double versus triple bond wouldn't matter, or lone pairs. And I specifically mean attached to the central atom. So really, I'm just combining tables 1 and 2 above for you. If we had 2 things attached to the central atom, and they were both atoms, so being more specific, if of those 2 things attached, 2 were atoms and there were no lone pairs on the central atom, that's when we call it linear for both its molecular and its electron geometry. If we have 3 electron domains, 3 things attached, and they're all atoms, none of them are lone pairs, that's when it's trigonal planar, or if you want to abbreviate, trig planar. And again, for its electron geometry, also trig planar. It's only when we start swapping some of those out for lone pairs that the molecular geometry changes. So if we still have 3 things attached, but only 2 of them are atoms and 1 of them's a lone pair on the central atom, so 2 atoms, 1 lone pair, its electron geometry, it's still 3 things attached, so we still would call it trig planar. Sorry, my handwriting is so messy for the electron geometry. But this one, its molecular geometry is called bent. Then everything that is 3 electron domains, whether it's trigonal planar or bent, whatever its molecular geometry is, it's going to have that angle of 120. And you just need to know that the less than sign would go there if there are any lone pairs on the central atom. So what I would do is I would go through and try to build this summary chart in your notes. Look at, let me scroll back up, make sure you've accounted for everything in table 2 and everything in table 1. But I think drawing some of those connections would help. If that doesn't help, let me know. We'll keep working at it.